Okay, thank you very much, Matt. Welcome all to the webinar, Advanced and Smart Engineering of Wind Turbine Foundations. Thank you all for joining. And on behalf of WindBASE and ABT, I would very much like to thank Diana and in particular Maas for inviting us to present this webinar. I would like to start off with some introductions. First, a little bit about myself. As Maas already explained, I work as a finite element specialist at ABT and recently also at WindBASE. I studied at the Eindhoven University of Technology. I did a bachelor's there in architecture, building and planning, followed by a master in structural design. And after that, I continued with a PhD study. The subject was post-tension masonry. And I did a combination of experimental and numerical research, resulting in my PhD thesis in 2013. And this period of PhD study was also my first experience with Diana. I should say quite extensive experience making material models in Fortran and things like that. But then after 12 years at university, I thought it was time to move to a commercial company. And I worked for 3 years as a structural engineer at steel, but also as a finite element specialist at IV Consult. And while I was working there for 2.5 years, I worked on the jacket lift system on the pioneering Spirit, which is the biggest decommissioning vessel in the world, which was obviously quite a challenging project. But then in 2016, I got the opportunity to coordinate all the finite element and advanced simulation work at ABT. Well, that seemed like a good next step. So since 2016, I now work at ABT. And when WindBASE was initiated in 2019, I naturally started doing my work for ABT, which involves wind turbine foundations under the name of WindBASE. ABT is an engineering company from the Netherlands. We are known for our multidisciplinary approach to engineering. We are not that big a company, about 300 employees, but we have worked on some prestigious projects, such as New Amsterdam Courthouse, Boijmans van Beuningen Museum, also recently a new terminal of Schiphol Airport, and many other projects. In 2019, as I explained, WindBASE was founded, and WindBASE is a company dedicated to wind energy, mainly the foundation design, which I'll be talking a lot about in the remainder of this webinar, but also expert opinions, design of civil infrastructure, and also risk management during the construction phase. WindBASE was founded because it's a recognizable brand in the wind energy world. And also it is more flexible in what it can offer clients compared to ABT when it comes to wind energy. In this picture, you see our WindBASE team visiting wind park Del, which is at the highway junction between the A2 and the A15 in the Netherlands. The team consists of many different disciplines. You see project leaders, structural engineers, geotechnical engineers, finite element specialists, site inspectors, and also developers. And even though WindBASE is a separate company, it consists for 100% out of ABT employees. And that's why in this picture you see a lot of the blue ABT helmets as well. Both WindBASE and ABT are part of the Oosterhof group, which is a holding with several other companies. And WindBASE is basically the front office for most of the world except for Germany and Belgium, where this function is filled in by EBD in Germany and ABT Belgium in Belgium. So after introducing myself and also the companies, I would like to show some recent projects that we did. What you see on this picture is the reinforcement for wind park Dell, one of the turbines, which you also saw in the team picture just before. This is a project with 11 wind turbines where we applied our standardized, so to say, piled foundation. But we don't do just projects in the Netherlands. Here is an example of a bigger wind park in South Africa, where we applied our standardized gravity foundations. Well, if a project falls outside of the scope of what we can deliver as kind of our standardized foundations, we will treat it as a special. This occurs also regularly. For example, in this case, you see here the Hartog channel in the Netherlands and the highway A15. And you can see the very narrow plot for the wind turbine foundation, which was obviously very challenging because it's very close to the canal and also very close to the highway. Another recent challenge was the project in Oostpolderdijk in the north of the Netherlands. Here, 3 wind turbines were placed on a primary sea dike. This is obviously very challenging because it is not just that you have to ensure the integrity of the wind turbine foundation, but also that of the sea dike below it. And a very unique approach was used here with CSM panels below the foundation block, which is very innovative and also beneficial for the earthquakes due to the gas depletion in Groningen that we also had to take into account in this project. So to summarize, WindBASE operates in the Netherlands but also abroad, and we have a current track record of over 3,000 wind turbine foundations in 27 different countries. Before digging deeper into wind turbine foundations and the use of Diana to analyze them, I would like to give a few examples of projects using Diana that we did at ABT. Why do we use Diana? For several reasons. It has suitable material models, in particular for concrete. You can use the 3D volume elements in addition to lower order elements. There are some advanced features like bond slip reinforcements and young hardening concrete, which are sometimes necessary to capture the complex behavior of concrete structures adequately. Diana is also recognized by Dutch authorities such as Rijkswaterstaat. And also we have over 20 years of experience with Diana at ABT. So some examples of projects. What you see on this project is a drink water tank where a new floor as part of a renovation project was poured on top of an old floor. In cases of these stage construction where new concrete is poured on top of old concrete, shrinkage is always an important point of attention. So what we did, we designed reinforcement to minimize the crack widths due to shrinkage within acceptable limits. And yeah, what you see in the picture on the right bottom is the reinforcement stress, which we try to control to minimize the shrinkage cracks. Another recent project was this dry dock, ship dock, where there is a underwater concrete floor with steel fibers. which is done in this way to avoid large cracks and therefore leakage. Especially in the length direction of this dock, it's very challenging to achieve this. And in Diana, you need a lot of nonlinearities and special features to be able to model this, such as all those that are listed. And this project is still going on as a research project to eventually come up with a guideline for this kind of structures. The hydration heat, the young hardening concrete in Diana, it can also be used to control the temperature in mass concrete, like this foundation block, which is, I think, roughly 9 times 13 meters in cross section. And here we inserted cooling pipes to make sure that the temperature differences within the block during pouring of the concrete and then setting of the concrete stayed within acceptable limits. And recently, Diana has been developing a lot of their geotechnical features. And here we did a project where we have a basement made of steel fiber reinforced concrete. And we modeled the soil structure interaction. Also, this basement was later tested. And we did also a comparison with the behavior of this model in both Diana and Plaxis, which is another geotechnical software. So then we come to the wind turbine foundations. Why do we do 3D nonlinear analysis of wind turbine foundations? What is actually a wind turbine foundation? It is actually the concrete block that needs to transfer the moments and the forces coming from the wind turbine and the tower to the soil. And depending on the soil, it's required to put piles below the foundation block. Or when the soil is good enough, it can just be a gravity-based structure. As explained before, WindBASE and ABT have a very long track record of wind turbine foundations. So you can see here that we did not start immediately with the 3D nonlinear finite element analysis. I think back in 1983, the year that I was born, that would have been rather difficult given the size of the models and the computers back then. So you can see that it developed 12 years later. We were making 2D plate models. And only in 2006, which is almost 15 years ago, we started doing the 3D nonlinear finite element models in Diana. So over the time, the complexity of our models has increased, but we also believe that the behavior that we capture now with our models is much closer to reality compared to the simplified models, which have a lot of assumptions regarding the internal force distribution. To explain that in a little bit more detail, I would like to first explain a little bit about a 2.5D model that we use in the preliminary phases of the design. This is actually a model with flat shell elements or curved shell elements and bar reinforcements. And by assigning the proper shell thickness functions, we get a geometry that looks and shape like a wind turbine foundation. This model can be calculated either linear, elastic, or non-linear. if you calculate the linear elastic, it gives you similar results to a model that you could make, for example, in SIA Engineer or any other software that allows linear elastic analysis of plate or shell elements. So here you see some results of linear elastic analysis of this model. What happens is that you get radial and tangential bending moments and also shear forces. And the normal engineering approach would then be to just translate these moments and shear forces into reinforcements. And of course, you can do that. It's a common approach, but it results in a lot of reinforcement, like in this drawing that you see here. So except for the section forces that you translate into reinforcements, you also have to take into account splitting or confining reinforcement and punching shear reinforcement, those kind of extra reinforcements separately, and all combined together that results in a lot of reinforcements. Also, this approach neglects the fact that the foundation is actually quite a stocky structure. And also it neglects the fact that upon cracking, the internal forces will redistribute. So for stocky structures, strut and tie models can be used according to the Eurocode, which is something that can be achieved, for example, in a 4-pile pile cap with some effort, but for a wind turbine foundation, it's quite difficult because it has a circular shape. It has a lot of piles. It can be up to 40 piles. And especially the tangential force path, which is quite important for wind turbine foundations, is difficult to capture properly in such a strut and tie model. So then we come to the 2.5D model in Diana with nonlinear material properties. Also, this 2.5D model, it still neglects the stocky nature of the foundation, but at least it is able to represent bending failure and internal force redistribution upon cracking and yielding appropriately. And the final station is the 3D nonlinear analysis. Obviously, this is the most complicated and also time-consuming of all the models. In addition to the bending reinforcement, also all the other reinforcements are explicitly included in the model. And also the post-tensioned anchor cage in the central part, which holds the tower, is also taken into account in the model. For the 3D model, we generally use a semi-probabilistic approach known as the ECOF method. So we determine for 2 load combinations and 2 different sets of material properties, we derive the actual capacity by doing a rotation-controlled analysis. And then we use the log normal distribution to calculate back to a design moment and compare that to the actual moment that is expected from the wind turbine. We also compared the 2.5D and 3D approach, and what we find is that actually the behavior in the beginning of the moment rotation diagram is very similar. The stiffness and also the gradual reduction of stiffness is quite similar, but we see that the 3D model has additional capacity, and we've seen that for several comparisons that we've made so far. So why is this? Well, as I explained before, the 2.5D model. It does not take into account the stocky nature of the wind turbine foundation. And strut and tie analogy cannot occur in a flat model. But as you see here, when it comes close to failure, you can see actually the compression struts becoming visual in Diana. If you look at a cross section, and also in the reinforcements, you can see the horizontal and the vertical tension ties, and together these form more or less the strut and tie model. But in the picture on the bottom, you see that there's also still a stress distribution in the tangential direction, because in the cross section, which is flat, the strut and tie method looks quite easy to reconstruct, but don't forget that there's also tangential forces, which are actually connecting all the strut and tie models that could be there in the different sections. But it is this strut and tie mechanism that occurs close to failure that is actually explaining the additional capacity in the 3D model. So what we've seen is that models with increasing complexity, they require more analysis time, but with each level, the behavior of the model comes closer to the reality, which is shown in a nice way in this graph from the model code. So by gaining insight in the complex structural behavior, it's possible, in our opinion, to reduce the modeling inaccuracy while still ensuring the design is still safe. So the load and material factors that are applied, or the safety philosophy that is used, it should ensure that we're not actually standing at the very edge of this waterfall. And also, with the integral approach that we use for the 3D nonlinear finite element analysis, it is less likely that we will overlook unexpected failure mechanisms. Because if you do a simplified approach, you have to be very sure to take into account all the local failures that could occur in the model as well. And if the Diana model is configured appropriately, then you will find these mechanisms as well. So there are several advantages of doing this more advanced approach. Obviously, we reduce material compared to the traditional design. So we can save quite a lot of cubes of concrete compared to some of our competitors, and also we can reduce reinforcement steel up to 40%. With this, we also reduce the environmental impact that our design has. Of course, the construction and material costs go down as well. And when we compare a WindBASE design to a traditional design, there is two steps in which are made savings. We do a site-specific geotechnical analysis, which results in savings, and then we do the 3D nonlinear finite element analysis, which results in more savings. The geotechnical analysis, by the way, is done not in Diana, but using other programs. Another important aspect is the constructability. We see sometimes some designs where there is a lot of rebars sticking vertically pointing up at the sky, which is not very safe. We see rebar configurations that are very dense and difficult to achieve in construction practice. Rebars with very large diameters that weigh over 100 kilograms per piece, which is of course not very friendly for the health of the construction workers. And in the WindBASE design, we tend to avoid these things to a minimum. Because we have less reinforcement, we also have less reinforcements which are vertically pointing at the sky. We also reduce the diameters to generally a maximum of 25 millimeter rebars, which is obviously much better for the construction workers. So, but of course, having talked about some benefits of doing this advanced analysis, there are also quite some challenges which you need to tackle to be able to apply this in commercial projects. The challenges are mainly falling under three different things. One is acceptance, the other is lead time, and another is budget. If we begin with the first one, then acceptance is quite important, because if you do a commercial project, then you make a design with an advanced model, you need to be sure that it is also accepted, for example, by a local government. And then you have to demonstrate that the approach that you do is actually equivalent to what is in the applicable codes and guidelines. You have also, you need to think about your safety philosophy that you apply, which can be a little bit different in advanced nonlinear analysis compared to a partial safety factor method that is generally found in Eurocode. And also important is who else can verify your advanced nonlinear analysis, because if you are going to compare it to a simple analysis following the Eurocode, it's difficult to compare the two. Validation of advanced models is also very important. For example, you can use some comparison to code calculations or comparisons to analytical calculations. Or if you have some experimental results or the opportunity to do some experiments yourself, you can use those to validate your models. We participate sometimes in blind competitions with sometimes a lot of success, like in this one, where we predicted the shear capacity of a poorly reinforced deep beam. Also, investigations when something collapses also gave a lot of knowledge, like here is a parking garage of Eindhoven Airport. And there were some experiments done at the TU Eindhoven to show the failure mechanism in the floors applied there. And then we reproduced these in Diana and also used Diana models with various strengthening methods to figure out which strengthening methods are efficient. And then later these predictions we did with the strengthening, they were also verified by additional experiments at Eindhoven University. This is a recent graduation project where we are using Diana to calculate various kinds of 4-pile caps. And as you can see, it's possible with Diana to capture very closely the behavior that is actually found in the experiment. Also, quite recently, we installed some measurement equipment in one of our wind turbine foundation designs. And we did measurements during an emergency stop. And we compared the strains and stresses in the measurements. We compared them to what we find in our Diana model. And the preliminary results are that there are quite some difference, and that is mainly because even though the foundation was loaded to 110% of the ULS moment, it was still uncracked. So further research into this is ongoing. Also at a more simple level, you can do various kinds of validations. Usually we make a moment curvature diagram from Diana using the same material properties and mesh size as we do in the actual model that we are making. And then we make a hand calculation of the moment curvature diagram so that we can show that the behavior is actually very similar. Also for shear you can vary things like the fracture energy of the concrete to see how that affects the shear capacity of, for example, a simple beam. And also in experiments with shear, you see that there is usually quite a high variation, and also between the various codes, as shown here. And then, usually when there is shear reinforcement present, this variation becomes less relevant. But explaining shear in a 3D model is always an important point of attention. So the other challenges are also lead time and budget. For a traditional design, no design iterations are required because you do your linear calculation and you have your internal forces and you determine your reinforcements and you are done. So the engineering costs, they can be quite low. However, the construction costs and time for construction, they will be larger because of what I showed before. Having models with lots of reinforcements which are difficult to construct. So the WindBASE approach is more advanced, and also because it's non-linear, usually some design iterations are required in which you can do optimizations. But a lot of time and money is saved in the construction phase. So in the end, even though the engineering might be more expensive, it's more beneficial for our clients. So I showed this slide once before. We've done a lot of projects, and our clients nowadays, they expect high quality, low risk, and short lead times. However, this comes also at a few challenges. For example, lead times of projects, they are too short to do innovation in the project. And sometimes the overview is missing which developments are the most valuable for our project, for our product. So that's why we recently shifted to product development, and we are still doing all our projects, which are also becoming more and more projects, but we are developing our project, our product continuously. So we are evaluating our projects. We evaluate what needs to be improved or developed, and then we are developing this each in its own time frame. And when it's done and it's successful, we adopt what we have learned into our projects again. So this approach is a different way of thinking, but it allows us to increase our product in a much faster and more efficient way. How do we do this? For example, we have WindBASE development days, which is let's say every 1.5 months or so, and we come together with our whole team, from director to engineer to site inspector to developer, and we present the recent developments, we discuss the new developments that are brought in, and we prioritize them. The required short lead times, they also make sure that we need to analyze our project and process workflow in a way that we can optimize and automate it. So we have one central source of input. Then we have a set of rules which translate this input to various kind of drawing and calculation models. And we even use it to automatically generate the report. Also, a decision that we made is to do the structural and geotechnical analysis completely in parallel to save lead time. And this results in a very efficient project workflow and short lead times for our clients, and still ensuring a consistent and high quality. Here you see an example output of a reinforcement drawing, a little section from it so that it is visible on the screen. And then here you see some piece of our Python framework that we use to generate the Diana models, which is done fully automatically. And in the end, we achieve a very consistent quality. Recently, also the site inspection report has been automated so that our site inspectors just have to make photos on the site and can upload them and make some comments in an app on their phone, and they can actually, they don't have to sit in the evenings making their inspection report. The short lead times of the projects also require that we make very efficient use of our Diana licenses. And our commercial projects, they should be prioritized above the research and the innovation projects. So what we did is we developed a tool that manages our use of Diana licenses. And in the future, we also want to add predictions of calculation times to it. We already made a start with that. So here you can see that there's kind of a linear relationship between the number of iterations times the number of degrees of freedom and the time in hours. Obviously, this allows us to better plan our calculations, but it also allows for optimization and comparison with different softwares. So the whole product development approach also makes sure that we have time to do research and innovation. So I want to give a few examples of that. For example, as I explained earlier, we are measuring in this wind turbine foundation that there is quite a big difference in what we are measuring and what our Diana model is telling us. So we believe this is mainly due to the hydration heat effects that occur when pouring the wind turbine foundation. So we have started a project where we are actually trying to take this into account in the analysis in Diana. So we first do a young hardening concrete phase, and then after that we go on with the structural loads to see if we can then come closer to the measurements. Optimizing construction is also something that we pay attention to, and the way our drawings are set up in an automated way, it also allows to create a manual, IKEA style, where we actually can say exactly to our clients, to the constructor, how we are going to actually build, for example, the reinforcement in a wind turbine foundation. Recently, we've also begun to extend our project workflow with a data loop. So the structured design data that we are creating is going into a database, and then we use business intelligence to get insight in previous project and make sure that our input for each project is so good that we avoid doing unnecessary design iterations. We learn also a lot by visualizing various results from old projects, by visualizing these in different ways. And we recently started also applying machine learning. We are first doing this by running a lot of 2.5D models. We have run around 2,500 of those using our Diana queues system, which optimizes the waiting queues for the licenses. And then we use the machine learning to predict, for example, the ultimate moment capacity based on the input parameters, or the other way around. And if this is successful, we will extend this approach to 3D models in the future. And then we can just put a configurator on our website where a client can come and upload their project specs. And the website will use the prediction model to tell them what kind of wind turbine foundation they need. And if then later they want to make some changes, they can do that. And if they need a final design, they can order that directly from the website. So this was what I wanted to share about WindBASE and ABT and the way we design wind turbine foundations. I hope you found it interesting, and I will be glad to answer as much of your questions as is possible within the time that is left.
Well, thank you, Lex. It was very interesting. So now we, I think, understood what's this state-of-the-art implementation towards the design of this type of applications. So Lex, once again, I would like to thank you for presenting this interesting topic. I see there are lots of interest towards this challenge, and I hope we could have you more in this type of, say, interactive discussions, and you bring the new ideas and the smart engineering concepts to the world. And also, I would like to thank all for joining this session and wish you a very good and pleasant day. Thank you very much and have a good day.